So hello everyone, welcome to the third lecture of the RISC-V class. Today we are going to talk about how to extend the ISA and the CPU based on RISC-V. But before that, let's do a quick recap. So the first day we talked about the RISC-V ISA. We learned that it's a spec. We learned how the spec is organized, what it includes, and so on. And we had a high-level idea of what the ISA is and what it's specifying. Then the second day, on Tuesday, we saw how to implement a few examples of CPUs based on the ISA. So we saw a big CPU that was really good in doing a lot of computations, designed for energy efficiency, with custom extensions, with a single cycle multiplier, and so on. And on the other extreme, we saw another CPU that instead was designed to be very small for control-oriented tasks, where, for example, many instructions were implemented in a multi-cycle fashion, and area and the leakage power were instead the key elements that were optimized. Still, both are RISC-V CPUs. And so we learned that the ISA is different than the implementation. The very first day, we also said that to get best energy efficiency, we have to do domain specialization. We saw adding custom blocks that are good in doing whatever you're trying to optimize, which always depends on the profile of your application. So we learned to answer like it depends whenever they ask you, is it this energy efficient, if you don't know the context. And today we are actually jumping into another example, which is actually part of the four-stage CPU. For what concerns domain specialization. So, as I said, domain specialization means adding custom hardware. In this specific context, means adding custom hardware. And here in this slide, we see an example of customization. Here in this example, I just wrote a simple C line, C code line, or whatever your favorite language is, which is A times B plus C, and then you put back the result in C. So you're accumulating a product in a single variable, which is, in this case, is called C. Is any one of you familiar with this kind of operation, which is the multiply and accumulate? And do you know where is it used? Examples?
Everywhere.
Everywhere, I would say, is the most common answer. Is if you're doing processing, so if you're doing data processing, 99.9% of the cases you get this guy. So indeed, yesterday when I walked through the posters, many people are optimizing Mac units. They are trying to get rid of the Mac multiplier, or they're optimizing its implementation, its representation, its number of bits, whatever, right? Why are you doing that? Because you want to be efficient in doing what? Why are you trying to optimize, for example, in your own research, for whoever is doing it, the Mac operation?
AI workload?
Yeah, but why you are not optimizing something else in this one, and you're optimizing the Mac?
That's the most used instruction.
Yes, it's most likely the thing that in your pie chart, in your profile, there's a guy that says he's profiling the application. It's probably the biggest slice of the cake. Okay, so that's why you're optimizing it, and you're doing it right. If your workload are machine learning workloads, if you're doing bubble sort or sorting of array, would you optimize your Mac unit? I'm not familiar with all the sorting algorithms, but unless there's some based on the Mac operation, yeah, unless there's a specific need for this instruction, I won't go for optimizing the Mac. So when you write this function, this operation, and you compile with your favorite compiler, whether this is LLVM, GCC, or whatever else, Here it's handwritten assembly, okay? So this is not exactly the output of the compiler, but I made it as readable as possible for you guys. This is more or less the code you get. So you're loading 3 values, A, B, and C. You multiply A and B. You store the multiplication in the result, and then you use the output of these results as an input of the addition instruction, sorry, and then you store back the result. Simple. Questions? That's how RISC-V will compile this operation. This assembly is not optimized for the architecture of any other CPU. Of course, if you have a stall, if your multiplication gets 2 cycles or it is in pipeline, you have a data dependency, maybe the compiler can fit something in between to hide the latency, whatever. Here it's just keeping simple. So one way to optimize, this is just an example, one way to optimize this code will be why not fusing the multiplier and the adder together in the data path. This is not a computer architectural class, so I'm not going to talk about in details about why this is efficient in hardware, why it's not costly in hardware, because more or less a multiplier and an adder cost the same number of gates into the critical path, okay? And the area changes marginally. So it's a win-win situation, but I don't want to go there. But if now you get, as I said, you get the same number of cycles, more or less, the same frequency, and similar area and power, in fusing those 2 operations, what is the advantage of the on the extended code? What is the advantage? And what are the disadvantages? There's never an advantage only. Can you please, guys, tell me? You are hired as a consultant in a company, and the company asks you what's the advantage and disadvantage of doing the things on the right.
The code is shorter and therefore.
And this is an advantage or disadvantage?
Advantage.
Okay, the code size is shorter. Good. And so you get all the benefits of having shorter code. Less memory requirements, more cache hit probability, instruction cache hit probability, and a lot of other stuff.
If you're doing a lot of them, you can dispatch one per cycle, even in a simple dispatch record. You don't have to do like mul add, where you get like half cycle, like 2 cycles per. You can do it every cycle.
Yeah, so, okay, you're talking about the computer architecture here, right? Because in theory, I can still execute the MAC as an add, as a mul and an add. That's implementation dependent. But yes, given the thing we said before, that you can fuse them and most likely you will execute them faster. I mean, you do 2 instructions in 1 cycle, is a way of increasing the IPC, correct? It's implementation dependent, but most likely it's the case. Others?
You need 1 less register?
1 more. Ah, 1 less in the compiler. Yes, okay, yes. You need 1 less register, so it means the compiler has more space for allocating it to something else. And therefore, there's a chance of using the stack 1 less time. But, as we are in the topic, a disadvantage is that most likely this instruction requires. Say again?
More access to the register file, maybe.
More, you're there, more? Read ports to the register file, correct. Because now you're reading 3 operands with 1 instruction. Again, implementation dependent, because you could still theoretically do access it in 2 cycles. So if you give up all the performance benefits and you only keep the instruction size benefit, that won't be a requirement theoretically. Okay, so we discussed a few of them. There are probably others, but yeah, that's what I want you to think of. There are advantages and disadvantages. Then there's another one, which is probably not clear here because you are not, let's say, doing it for real or for long term. But how do I compile the code now? What do I need to do? Exactly. So you have to modify the compiler. So modifying the ISA means also modifying the compiler that you need to maintain. It's not that no one else is maintaining your own compiler. It's you, your company, your foundation, whatever. But it's your business, right? You have the freedom of doing it, but you have the duty of maintaining it. Otherwise, your code won't work. That's one thing. And once you want to do it, we discussed this the other day. Also, if you are designing your own CPU, you have to find the space in the decoding space that there is, but still you have to keep it into account, extending the decoder, adding eventually or possibly this extra read-write port to the register file, or complexify the controller. So adding an extension, of course, it's immediate to think about the benefits, but you also have some disadvantage that you may want to think of ahead. But most likely you have more disadvantages than disadvantages, otherwise we won't be here teaching this part and people won't do it, right? But that's one way of doing domain specialization and hitting higher energy efficiency, but you need to do it carefully. So the first example we are talking about today are the custom PULP extensions. Most likely you talk with the guys at the end of this room that are from the PULP group of the Bologna side. But basically PULP is a project that was born 12 years ago between two universities, University of Bologna and ETH Zurich. And among their goals for achieving higher energy efficiency, we extended, as I was part of it, the RISC-V ISA with a lot of instructions, and we will see some of those examples now. So the goal of the PULP project was doing high energy efficient edge device platform and with a multi-core architecture. So you already have the performance advantages of parallelism. Why parallelism? Because most of the workload, as we discussed the first day, at the edge are data analytics tasks that are very easy to parallelize. Usually they parallelize naturally. And so already like that you get higher performance. But then if you specialize even each of the core of the multi-core platform, you can, each core is much more performant. And now we are going to discuss few of these extensions. We already touched a bit of them 2 days ago during the RISC-V implementation details, but you should have already a feeling about what are the kinds of instructions we are going to talk about. Are those crypto extensions for security? No. Are other kind of extensions that are for other kind of domains that you can think of? Do you guys know any extensions for whatever other CPU, either it's a RISC-V or not?
Yes, is doing genomic extensions.
Okay, genomic extensions, yes. So you see they have a name, right? It's a domain specialization. Okay, so these ones are for data processing at the edge. So they are really thought for this profile. These ones are divided in three main sets. You have the general purpose one that are usually beneficial for many of different applications. So whatever I just said that are domain specialized, it's broken in the first sentence because here I'm saying they are general purpose. And the reason of adding general purpose extension is just to boost a bit the normal code, I would say, without paying too much of hardware overhead. So those are things that make sense in your own context. So those are implementation-dependent ISA extensions that make sense from an energy point of view, from a wider number of applications than the simple data processing. Then you have bit manipulations, and bit manipulations in general, but especially in, when you deal with peripherals and control code, are useful extensions to manipulate the single bit in a word. For example, give me the bit number 3 of this of the register number 5. How will you do it in C? You have to shift and then do the AND, right? Okay, those is 2 operations. So those are instructions that fuse these things all together, or set to 1 the bit number 28 of this register. What will you do is putting 1, shifting 28, and then you do the OR. Like this, you fuse it in 1. And then finally, you have the ones that matters the most for our domain, that are the digital signal processing ones. Okay, so we are now going through a few of those extensions, and we discuss together what are the pros and cons. And we do the same discussions over and over. But hopefully towards the end you get bored and you immediately reply what makes sense and what doesn't, or what are the costs, at least. So this has been mentioned probably by you before, or no, someone said yesterday 2 write ports. Who was the 2 write ports person? I don't remember. You?
I think so.
Okay. So this one is an extension that I already mentioned a disadvantage, which is the 2 write ports, which is automatically incrementing the address of a load or a store operation. Why does it make sense? If I wrote it, don't read it. Probably I wrote it, but try to think with your own mind. You have the assembly there. So of course, the code sides will always be true as an answer, so we don't say that in every instruction.
For doing address calculation when you're accessing stuff from an array.
From an array, exactly. Your colleague answered processing array, where array is the C array, or the language, a vector, I would say, for an application vector, that in C usually are implemented as array that are continuous in memory. What would you write in C? For I equal to 0, I less than n, I plus plus. Then you index your operands, and you put them back in the accumulator or another vector or whatever, whether this is a reduction operation or a element-wise operation. But what is common is that you load, and then you update the address by 4 if those are 32 bits, by 2 if those are shorts, by 1 if those are char or byte. So this is a frequent pattern which happens in all the time you deal with arrays. With the linked list will be slightly different, of course, because the update is not a constant. But with arrays, it's always the size of your own element of the array. So if you fuse them, load and add, you get rid of an instruction for each load, and this is the same for store. When I say load, I also mean store. You do an extra, you fuse the instructions, so in your data path you are both emitting an address, and you tell the other to do this guy plus 4, or plus 2 plus 1. Then the memory responds with whatever you loaded, but also the adder gives you back the updated address. So at this point, either you sequence the writes back to the register file, or as we decided, you add a write ports and you write 2 things in parallel. You have a question?
So it loads the original address?
Yes.
Okay, because that's not the opposite for how they do it in ARM, but I don't...
No, I think it's the original address, although I don't know it by heart, but I'm quite sure. Yeah, but I guess it's the original address, yes. I'm quite sure. Okay, so imagine you have many vectors in your innermost loop of your application. You are saving the one instruction every iteration of the innermost loop. And if you are familiar with AI or DSP or linear algebra kernels, usually you have nested loops, like the matrix multiplication, you have 3, for example. And within the innermost loop, you have n to the 3. Imagine those matrix multiplication are squared. Number of instructions saved. I mean, not execution of instructions saved for each of these operations, which is a lot, right? So if you take it at application level, if I get just this piece of assembly, it's like I saving 2 instructions. What do I do with 2 instructions? It's not too much. Who cares? But now if you execute this in an innermost loop with 2, 3, 4 nested loops, this starts becoming a big saving, both in performance and in energy. Questions?
Does this support early exit?
Yes, I would say yes.
How is it handled?
It's by the compiler. So you mean if something breaks
Yes.
in the innermost loop? Let me think. Actually, yes, you shouldn't change anything, because in the end, as long as the compiler knows that this guy has been updated, if he wants to reuse the address, it will compile it in a way or in another. So if, for example, if you need the address to be as it was before being incremented, if a condition is true, the compiler won't choose this instruction. If you don't need the original address, then why not? It's up to the compiler, right?
So did you combine this with the loop buffer, or is it only using this kind of indexing calculation? So it doesn't statically allocate these instructions in the instructions tree?
I don't understand the question.
Did you also use a loop buffer with this extent?
A load buffer?
Loop buffer.
Ah, loop buffer. No. No. Those are normal loads as any other RISC.
I mean this hardware loop.
Ah, okay, but you are in the hardware loop. I'm not talking about the hardware loop. So that's why I was so confused. Okay.
Sorry.
No, the hardware loop we discuss later, yes. But the answer is no. Questions? If not, now we go to the hardware loop. So that is another thing that happens very frequently in your code. That's why those are general purpose things, right? So again, if you have loops, what do you do with normal RISC-V or normal ISA, I would say, standard ISA? You have a counter that is counting the iterations, a counter that, or a register or a constant value that holds the number of maximum iterations, so our n friend in the for loop. And then within the loop, you do your own stuff, which are whatever you are executing in the innermost loop. And before finishing the loop, or somewhere, but before it ends, the iteration, you have to decrement or increment the counter, compare against the limit, n, and then decide whether to take or not the branch. So n minus 1 of times the branch is taken, the last time is not taken, right? So this has a penalty. And I try to emphasize this by saying you need a counter, you have to initialize it, then you have to decrement, then you have to compare. Okay, so if the loop is really big, it contains 1,000 instructions, it doesn't really matter if you're wasting 1 or 2 instructions to do that. But if your loop is small, 2, 3 instructions, 4, now the extra 2 instructions is a lot compared to the innermost kernel. So the useful computation gets diluted quite a lot by the branch and by the comparison and so on. So that's why in embedded system that runs, or in application that runs very small loop, and for example the dot product, which is just C plus equal to AI times BI, that's 1 operation or 2, let's say. For this kind of applications, having an hardware loop, meaning that a finite state machine within the CPU that doesn't really, that knows the number of iterations ahead, knows the start and the end, makes sense. Because you can get rid, from the software point of view, of all the overheads we just discussed. How it works? So what we did was adding 3 special registers, start, stop, address. So address are instruction addresses. So you know when the FSM starts, and you know what's the last instruction, such that you can branch ahead at the beginning of the loop. That's why the end is needed. And also you need to know when to stop. And the number of iterations. Like this, you set these 3 instructions, or these 3 special purpose registers, and now the CPU knows when to branch back, how many times, and when to start doing that. In our specific case, we added 2 of them, so you can do that in 2 nested loops, but not in 3. Why not in 3? Or 4, 5?
You checked your use case and found that it didn't make sense because
Exact, empirically.
not that many
Profiling. Maybe if you have the third loop, the impact of performance is marginal with respect to the first and the second one, right? Because in the matmul case, it's n times. The second one is n squared, and the innermost is n to the power of 3. So the one of n, who cares? Plus is bigger, because it's doing a lot of stuff within. But of course, you can add 3. If it makes sense for you, you can do it.
Can the loop number of iterations be a register, or does it have to be an immediate value?
Both.
Okay.
You have both the options. Of course, to go back to your colleague's answer, there are limits. Can you break it? No, because you break the FSM within. So you need some assumptions. So you don't have break. You don't have if condition break. You don't have jumps.
So you can't even within the loop do any jumps?
No. Forbidden. So if you do it, the FSM recognizes it and traps. Illegal sequence. So whenever the compiler needs to do it, it won't choose the hardware loop. Another limit we personally added was instruction must be aligned. Do you have to do it? No, it was to simplify the FSM, because otherwise, am I jumping back to a misaligned or aligned? Is the ending aligned or misaligned? When is the end address? When do I jump? So the FSM was very error prone and with a lot of states. So we said, okay, let's simplify the hardware, and we waste a bit of instruction space in case there were opportunities to use complex instructions. Those are the trade-offs you do with the implementations. Of course, you can get interrupts. This is allowed, because those are asynchronous events. You don't know whether you're getting an interrupt or not. So when you jump to the interrupt service routine, what's the disadvantage?
Sorry, can you repeat?
When you jump to the interrupt service routine, what are the disadvantages of having the hardware loop? Okay, no, not you two. let someone try. Someone else.
Store the state machine states, I guess.
Yes, correct. You have 3 extra registers to save in the context. Or if you're doing multi-threading, similar thing, right? You have 3 extra registers. So now whenever you jump, it's not, you don't have to do the 32 push to the stack, or 31, because 0 is 0. You have to do 31 plus 3. Because when you come back, the FSM needs to know the number of iterations it did, right? And it needs to know the start and ending address, in case it gets overwritten in the ISR. That's one disadvantage. Another disadvantage?
You need the hardware to check addresses. Like, I don't know if that's expensive, but you need it at least.
Yeah. In more general, it's true, but just one more general, more generic disadvantage.
I guess more area to implement the state machine.
Yeah, it's the same, more area, more power, more general. Complexity. It's not, the hardware loop is often found in DSP processor, whoever is familiar with, but it's not very common in out-of-order cores or superscalar cores, or because the controller of these guys gives quite some headache.
Yeah, also because like if you have out of order and speculative execution and everything, you can get the same result with these features, let's say. But I guess here it makes sense just because we are in a like super low power environment, and so you like give up all the riskiness, but just
Yeah, which is the reason why you find them in DSPs, because they have the same context. Low power, efficient,
Yeah, this is basically
single issue.
level 1 plus things in our class.
Yeah.
Does the XPULP extensions include any conditional execution that's not based on branching, but just like do this only if register is 0?
No, we didn't implement conditional instructions. And the RISC-V doesn't also specify them.
Yeah, because you don't have them, so you can't do any kind of
No.
inside the loop.
No. Good. Bit manipulation. I mentioned them at the beginning, so you need to manipulate the bit. And those are very popular in when you deal with peripherals. You know, you have to read a status register of a peripheral, where in the bit 29 it's written if the peripheral is ready, and in the bit 25 it's written whether the peripheral has a pending interrupt to be served, and so on and so on. So when in embedded system you deal a lot with peripherals, well, also in general CPUs deals a lot with that. So that is one example where they get a lot of benefits. But also in the example we said 2 days ago, when you have to count the number of ones in a word, this is also, for example, the example I'm printing in this slide. So we added a pop count instruction, which is simply another tree of single bits. Those are very popular in binary neural network, or in general when you have control code and you have to, for example, check how many cores synchronized in a barrier because they are setting one when they are waiting. And so you want this register to be equal to F if the cores are 4, for example. Or for handling priority stuff, find the first one, find the last one. So you know exactly which index has the highest priority, and so on. Now we leave the more. You have a question? Yeah.
And there's also the RISC-V bit manipulation.
Yeah. Okay. Good. Thanks for the question. Let me answer that. So when we ratified these instructions, and this is also true for the next instructions, RISC-V didn't specify yet the RVB standard extensions. So we worked in parallel. We started drafting these extensions before RISC-V. And today they are not the same, of course, right? Because you do your own. They have a lot of things in common. I won't be able to discuss exactly all the details, but they are not the same. They have a lot of similarities. Most of them can overlap or slightly change the meaning, but they are not the same. So this CPU won't be able to run code compiled with RVB flag on. It will trap to an illegal extension, to an illegal instruction, and vice versa. If you buy a CPU or you design a CPU complying with RVB standard from RISC-V and you run this code, it won't be running correctly. Okay. This is true also for the next extensions with the DSP. Similarly to the RVB, RISC-V is also ratifying the RVP packet SIMD. They started discussing the RVP, if I'm not wrong, in 2018, but these guys have been designing in 2015. So again, they're not the same. Again, there are a lot of things that are in common, a lot. And there are actually currently open source projects that try to merge the two in a single CPU with basically aliasing for some of the instructions and so on, but they are not the same. They have some differences. Some of them are important, like 64-bit operations and so on. Some others are just very, very similar, and you just need to change the encoding. Because this encoding is in the custom space, whereas RVB and RVP are into the standard encoding space. But apart from that, many of them would overlap, so the data path won't be different too much. So which kind of extensions do we find under the DSP extensions? So how many of you use fixed point instructions? Or operations, not instructions, operations? Okay. Few people. They are the unlucky ones because it's difficult to use fixed point. It's the user, is the developer that needs to take into account the precisions and of the bits, while with floating point operations, it's mostly done by the representation of the number as the point is floating, so it's moving. While it's fixed point, it's you that needs to take into account what the meaning of every word and whether to adjust in case of going out of the bit width. So when you do that and you write the code, you have to do a lot of additions, shift, rounding, and it's quite boring, I would say. But it's very useful from what concerns the energy efficiency, because you don't have the extra hardware, which is usually expensive, to compute floating point numbers. So a floating point adder is usually more expensive in terms of energy and power and also in performance than a fixed point adder, which is an integer adder plus or minus. Similar with subtraction, comparisons, divisions, multiplications, and so on. So a fixed point makes sense because they are cheaper. If the precision allows you to use a fixed point representation, which is often the case in embedded applications because the sensors usually don't have a very high precision, usually they count with 12 bits, 16 bits, and so on, then using fixed point makes sense. So it makes sense to speed up some of the common operations. For example, when you do a fixed point addition, you also round, and you shift to adjust the precision, and so on and so forth. So we fused all these instructions, and we say add with the rounding and normalizations. This is what add R and N means, for example. Or you round without normalizing, or you normalize without the rounding, and so on and so forth. And this is done for addition, subtractions, obviously comparison is not needed, it's the same as the integer one, multiplications, and that's it, division is not done. Other kind of, yeah, you have a question.
How do you encode the fixed number of bits in your instruction? Is it registered, an immediate?
Both. We have both the versions. So the question was like, how do you encode the amount of bits to be shifted? It's either in a third register, as we now have 3 read ports anyway, or it's an immediate.
I'm not that familiar with fixed point, but do you need to normalize after adding? Is there a shifting after?
Yeah, that's what the code does. It's adding and shifting back. But you don't have to, it depends on the representation. This is one example. But you don't need to. If you want, you're adding 2 numbers, now your number is 1 extra bit larger, in the worst case. And you can also say, this is my representation, it's fine. So you were adding 2 Q1.1 numbers, you have a Q2.1 number, it's fine. But if you still need 2 bits, then you have to shift, because you want to get rid of the LS bit, not of the MS bit, right? Or you saturate.
Yes.
Okay. So other kind of instructions I was indeed about to say are absolute of a number, minimum, maximum, saturation, MSU, which is multiply and subtract instead of accumulate. And there are others that are into the FFT domain, so when you have to rearrange the butterflies. So there are a lot of these instructions. They are open source. The spec is open source. You find them into the Open Hardware Group CV32E40P documentation. As I told you, this is implemented in the CV32E40P. The implementations is also open source because the core is open source. The compiler is open source. So you can, from today, you can start using the CPU with these extensions, and maybe in your research can be useful for your own applications, or maybe you can play with the compiler and the core and adding more or removing some, or modifying some of them. Of course, when you start adding all these instructions, areas start becoming pricing. You have to be careful. So when you design this stuff, you need to know in depth what's your architecture and what's your data path, really in detail. Because you don't want to start adding adders, comparators, multipliers, like crazy, right? You want to share resources. So this is what you will find into the RTL description of the core. It's just, maybe it's less readable, but then you say, okay, the shifter used by the add and shift instruction. Of course, it's the same shifter that you use for shifting, right? You're not using them at the same time. So you are sharing the resources. What's the disadvantage?
Maybe it will take more cycle to execute like this instruction.
Could be. Why? Why it will take more
cycles?
cycles?
In use, like while you have to execute the other instruction, then you have to wait.
Okay, but in the, so your colleague is suggesting that as the core could doing the shifting in parallel, you have to wait, so you have to execute the instruction in multi-cycle, but in this case it's a single issue in order core, so it will never be the case.
Okay, so in that case maybe like since you cannot be sure you have always like in some cases you could do it early, but since you have only one, like
No, I didn't understand, but I'm not sure you're going to the right direction. It was better you were closer before you were closer.
Critical path?
Critical path, correct. Before you had an adder whose results was going to the register file and a shifter whose result was going to the register file. Now you have an adder whose result goes to the shifter, whose result goes to the register file. So your logic is deeper, isn't it? So this could increase the frequency of your, decrease the frequency of your CPU, increase the clock period. So before adding it, you do it, you do the physical implementation, you check, and only then you decide whether to include this instruction or not, or if you want to include it in a single cycle or not. So when you design extensions, you always have to design them, co-design them with both the software to understand whether your application can actually make use of whatever you're thinking, with the compiler to understand whether the compiler can digest these kind of instructions and emit them automatically, or if you have to write assembly or low-level C code with built-ins, and with the physical design flow to check whether your implementation is actually beneficial for your execution. Because in this example, imagine you do the 3 instructions in 3 cycles, add, and shift, and for whatever strange and unrealistic reason, the instruction on the right takes 4 cycles, then you're losing performance instead of gaining performance. You are still decreasing code size, but maybe you lose performance. It's not the case, and it's a stupid example, but this could happen. That you are adding one instruction and then you go slower. Maybe because you didn't optimize the implementation. Okay? So this is to give you an idea. You have a question? One second. To give you an idea that adding extensions is an hardware and software co-design, which includes application, compilation, implementation, and physical design. So it's a long process. And if you guys participate to the RISC-V working groups as a member, and you have access to all the working groups where they discuss, shall we add these extensions, shall we add other extensions into the standard RISC-V, you will see that most of the discussions are in these 4 points. Is it useful for the application? Can the compiler use it with this definition, or we need to change a bit the definition of that? Is the physical implementation make sense? In general, of course, not for your single CPU. You have to make an agreement with out of order superscalar guys with the small tiny CPU. And there is no one fit all solution. So you start doing trade-off, you start arguing, you start making examples. And that is the same thing. In this case, it happened within the same team. So I was the hardware designing, fighting with the compiler person. And we changed a lot of the instructions because I was coming back with, this is bad in area, this is bad in frequency. Let's change the definition. Let's split it in different instructions, and vice versa. When I was proposing something, he will come back and say, the compiler doesn't like this thing. Let's define it like that. One example is the hardware loop. That the end address of the hardware loop is the instruction after the loop. Don't ask me why, because I'm not a compiler guy, but or maybe some of you knows, but apparently the compilers like that you define the end of the loop as the instruction following, so the +4, not the instruction itself. Why? No idea. I just say okay, and it doesn't really matter. It means I have to compare with something +4 instead of that guy in my final state machine, but or -4 actually, but if makes the compiler's life easier, in hardware doesn't really matter much, so let's do it. And those are the compromise and things you need to do.
How are you able to encode 3 registers and an immediate value? Do you have your own funky encoding for the X there?
Where is the X?
No, the add RN has 3.
The extensions. Yeah, of course you define your own encoding, yes.
It's not like the L encoding? Like
No, you define your own. We try to do it, but sometimes you can't. So yeah, so you complexify the decoder. Absolutely yes. If I didn't say that, the decoder, we said that at the beginning, I guess, of these lectures, but the decoder is always becoming more and more complex because it has to decode more instructions. So there are more cases in your switch case to translate it in code. Okay, questions so far? Because now we change a little bit, we change a little bit the nature of the extensions.
I have a more general question. Are we allowed in, for example, in the case of Mac in the RISC-V, having a bigger registers for Mac results, or this kind of?
Okay, so the question is, can I add extra registers into the ISA to hold, for example, the accumulation of the register of the Mac operation? So the short answer is no, but it's not true. So no means the registers are 32. So if you want to go for 33 and you're talking about the general purpose registers, then you will change all the decoding for an extra bit. It will be a little bit strange. You can do that by using the special purpose register, the CSR in the RISC-V language. So that you can do it, yes. So you can do it, but I never saw anyone doing it with the general purpose ones. So the X33, I never saw it, or 32, sorry, because it's from 0 to 31. So I never saw anyone adding X32 or the X33, but a special purpose register, definitely yes. You can do whatever you want in that case. You define an extra register, you define a semantic. Of course, once you have to store it, you need to move it to the general purpose one and then to do the store. You will do your own calculations and your own profiling, and you will figure out whether this makes sense. But for sure, this will save a register port, for example, or a read the register port. For us, it doesn't matter because we had many instructions that needs 3 operands. So once you add one, it's fine. But if it's only one, then maybe a special purpose register makes sense, more than this solution.
And what I meant is more like the registers that instead of 32 bits are 64 bits, so it's going.
Okay. So there's a name for this. I don't recall the name, but yeah, appending X0 and X1 and X2 and X3, and they become a 64-bit registers. Yes, this is what standard RISC-V RVP extensions do. So if you look at the packet SIM, the DSP extensions of standard RISC-V, if you recall at the beginning I said we are similar to that, but they have 64-bit operations. They do it like that. So when they write back 64-bit operands, they do it by addressing 2 consecutive registers. So you have only 16 registers in that case, because they are all twice the bit width. So that's why you have 16. Yes. So you think I like the RVP of RISC-V? We didn't. So you can. Actually, they do it. So remaining into the DSP packet SIMD extensions. What are packet SIMD? I mentioned it, I guess, a few days ago. So first of all, what is SIMD? Raise your hands, whoever knows what SIMD is. Everyone. Perfect. Many of you. So SIMD means with one instruction, single instruction, you process multiple data. So when I say I have a SIMD addition, means that my addition is not referring to a scalar value. Is referring most likely to a vector, or whatever multi-data means. That's SIMD in general. Now, how to implement SIMD? We have 40 plus years of research here, so there's no like this, there won't be an answer. But one way is with the SIMD machine, which means you load n words from a SIMD load would read multiple elements, multiple data, to keep on using the SIMD word, store the multiple data in a multiple elements registers, so a wider registers, and then when you do the SIMD addition, you read these multiple elements, you add them, and you store all the element-wise operations back into the register file. That will be the simplest SIMD machine. For sure it's not the most efficient, but it's the simplest to think of. So if you do the exercise 101 in computer architecture, the first example of a SIMD machine will be something similar to what I said. Okay. Packet SIMD are exactly the description of what I said, but they don't increase the size of the register file, which means that the maximum element that you can store in a register file is equal to anyone?
What do you mean the size?
The maximum number of elements that you can store in a register file are equal to?
Less than 32 for sure.
32, less than 32 elements.
Or 8 bits.
What did you say?
Or 8 bits.
Maximum number is for 8 bits. Who else?
Depends on the word size. Depends on the word.
Better answer, depends on the word size, okay?
992 bits. They were
No, this one is better, it's missing an extra info. Depends on 2 things.
And the bytes.
And the
The bytes.
the bytes.
The number of word and to maximum is the number of bytes.
Depends on the word bits and think of how many elements can you store in 32-bit? 32 bits, but how many elements?
If you consider the byte as the smallest size, it's up to 4.
If. It depends on the element width. Otherwise, you cannot do the division. 32 divided by 8 is 4. So someone said 4 8-bit. True. But who said that the elements were 8-bit? And who says that the word was 32? So it depends on the word length and depends on the element length. You can also do sub-bytes, and there are actually the team down there in Bologna extended this with sub-bytes operations with 2, 1, 4 bits. Now I don't recall if 1 was included, but 2 and 4 for sure. That will be more than 4 elements, right? It will be 8 or 16. In this specific example, we decided to be C-friendly, C-code friendly, so char short word. As the machine is 32-bit, there is no 64-bit elements. So in 32-bit, you can put one 32-bit element. That will be the scalar version of my vector. 2 16-bit elements or 4 8-bit elements. And now that I defined these three kind of data types, how do I do an addition? How do I tell my CPU, now add these guys? The answer is,
Just use the other and go to the carry chain.
that is one answer, but the usual answer is, depends, right? It always depends. So how do I tell my CPU, do this addition? How can the CPU know if what to do when you tell the CPU add?
Do you use a different add instruction?
That's one way, and SIMD machines usually do that. They specify an instruction for each element width. So in this case, you have three different instructions. A scalar instruction, standard RISC-V, 2 elements, 16-bit instructions, custom, 4 elements, 8-bit additions, second custom extensions. The other way is, of course, must be different than this one, otherwise I wouldn't have said the other way is. Correct. Having a status registers that tells you whether you are into the 8-bit, 16-bit, or 32-bit case. I've seen both implemented. And in RISC-V, both exist. One is for vectors. They write into a custom register what's the vector length in a register called VLAN. And while this packet SIMD, that is the vector philosophy, while the SIMD philosophy is encoding it into the instructions, the bit width, the element bits. So you don't need the state because it's encoded in the instructions. Pros and cons. Someone tells me the pro, and from this side, and someone the cons from the other side. Pro of using a separate extension instructions for each of the bit width.
One less register.
Yeah, so one less registers to keep the state. And
You don't have to write to the CSR to change.
exactly. I can interleave these instructions without changing the context. I don't have to say, I'm doing 16 bits, now I'm 8, now I'm 16, now I'm 8, now I'm 16, then I'm 8, now I'm 32. So if you do that frequently, very bad idea. So your colleague is right, and your colleague is right, you don't have the state register. That you will need also to save in the context of an interrupt in case. Those are you were the pro, right? The pro of the vector way, or the cons of the SIMD one, they usually are orthogonal.
You take it more opcodes to encode all the different.
Perfect, exactly. Exactly. With 3 possibilities, it's 3 instructions. And if I have 1,000 of elements, do I need to add 1,000 of instructions? Sooner or later I will finish the encoding space. Exactly that, correct. So in that case, hopefully your code is not interleaving vector length, otherwise you end up with what your colleague was suggesting, but yeah, you have a status registers and you have a single instruction, only one. Okay. Data path, how do I implement this guy? I have a RISC-V CPU with a 32-bit adder. I chose to do packet SIMD extensions. So we are not anymore talking about vectors. We are talking about doing 16 bits or 8 bits additions. How do I implement this guy?
I can reverse where you got the carries between the
Yeah, exactly. Also the gentleman down there suggested that, so you both answer the same thing. So you can have the same number of adders if you want, 8-bit. And then depending on the instructions, you propagate or not the carry. You stop the 4 carries in 8-bit. You stop every second carry in 16-bit. You don't stop any of them in the 32-bit one because you want the carry chain to propagate. This is exactly how it has been implemented. And why I didn't go for 2 16-bit and then 4 8-bit adders? Why didn't I go for the simpler way of describing it?
More area?
More area, yeah.
But in this case, we lose the carry flag or we save...
There is no carry flag in RISC-V. It doesn't exist.
It doesn't exist.
And you wouldn't lose it in the 32-bit case, if there was any. But in the 16 and 8, yes, you would have lost it. But there is none. In RISC-V, there is delegated to software to check if the instruction overflowed, which I like as an hardware designer. Less things to do. So area. Who said area? I don't recall. Yeah, saving area. You try to save resources. Of course, I decrease the critical path, right? Because I'm putting an AND gate in the carry chain. So I'm increasing the carry propagation. But if the frequency doesn't decrease, who cares, right? That's the co-design you need to take care of. Okay, I'm late. This is an example of whatever I said now. This is like including all the extensions that we talk today. So we have load with auto increment, then I'm adding an hardware loop, and then I'm finally adding the SIMD addition. As you see, code size decrease. Remember that when you go for packet SIMD, you are doing 4 times more operations, so the number of iterations is 25 now. This is the partial parallelization. Good. This was an example on how to do 2D convolutions. Now you can packet more things into the registers. So packet SIMD is also good because as you packet more elements within the same register file, you need less registers. If you have a 5x5 window, you need 25 registers, right? But if you packet them in a register, you need 5x5 divided by, you group them by 4, right? So you need less. And in this example that I let you read, and you can ask me questions about, maybe tomorrow when you digest the code, this is how to do the 2D convolution with packet SIMD. Another cons is that the code is slightly less readable. Slightly, it's still readable, but it's not really writing plain C code. Usually you have to help the compiler. Okay, another example, which is under discussion now in the RISC-V community, it's a very hot topic, is let's rectify matrix extensions. So vectors are 1D data structures, matrices are 2D data structures. And if you participate to the RISC-V working groups, they're discussing a lot about that. Why? AI, correct. Correct. Matrices as vectors are very common in linear algebra, AI, and every DSP-like kernel. So having custom extensions, not custom, they won't be custom anymore once they rectify that, but having dedicated extensions playing with the 2D data structures will simplify both the code and will speed up the execution. So in this case, we started 1 year ago and we published the paper like a few months ago. We started implementing something. We started from one of the first draft. This draft is changing every other week. So this is for sure not compliant, but there's no spec now, so nothing is compliant today. But basically what these extensions are defining is 8 extra registers. I didn't say that before. Packet SIMD registers are the same scalar registers. Vectors, no. Vector registers have a dedicated register file. This is also a dedicated register file, but it's 2D, where you define the number of rows and columns of this register file. And then what you can do, you can load, you give the starting point of the matrix and when to go back, because now they're not continuous in memory anymore. Every row they jump. The stride, correct. They can also be continuous in memory, but you still need the stride to know when the columns ends. Otherwise, mathematically, how can you implement the math mul if it was unrolled? Then you can do the MAC. But what does MAC mean when you have two matrices? Math mul. And the systolic array is one way, it's not the only one, but it's one of the most efficient way to compute matrix multiplication. So now you have your matrix register file that contains in each of the 8, in this case RISC-V is going for 8 matrix registers, the matrix or the sub-matrix of your bigger matrix. And then when you do MAC, the systolic array reads the register file, matrix A, matrix B, and matrix C, A times B plus C, and then the results goes back. You can also do matrix multiplication only without the accumulation, of course. Then what else? Yeah, you load them, you store them, and then you can do element-wise additions, subtractions. We didn't implement them yet because those are as efficient as the vector ones, right? Element-wise operations, whether they are 2 or 1 bit, it's a similar operation that you're doing. What changes is the 2D operation, which is the math mul. But the matrix addition is exactly the vector addition, right?
I have a question. Is there any smart way to implement math mul and accumulate with systolic array? Because I know that you can do much multiplication with systolic array.
When you accumulate in a preloaded accumulator. So when A and B comes, you multiply and accumulate into the preloaded registers, and then when you stream out the results.
Okay, so you initialize them with C? And then
Correct. Or B, I don't recall if you initialize it with C or B, but it's either weight stationary or input stationary, output stationary. It depends on the strategy you're using. And but yes, you initialize one of them and then you continue.
Just at the cost of more area?
Yeah, not marginal with respect to the whole systolic array, so it makes sense. Questions?
So, this is implemented as a coprocessor or as a part of
in this specific case, we implemented it as a coprocessor, so it's not part of the CV40P. We have an extra coprocessor called Quadrilatero, which is a district in Turin, that's why I call it. And it's a square, we mean square, something squared in Italian, which reminds the matrix. And both the designer and me are from Turin, so we decided to give Quadrilatero as a name. And it is a coprocessor complying with the X interface from Open Hardware Group, hosted into the PULP platform GitHub repositories.
Is the Mavic extension that the RISC-V Foundation is looking for will follow this type of custom instructions?
Yeah, of course. No, we read it from there, yeah. But it's not ratified yet. So as long as it's not ratified, it's a custom extensions. Then we cherry-picked what we needed, we modified slightly the meaning, but it doesn't really make any big difference. If it's not ratified, it's custom. So there's no halfway of doing it. It's either RISC-V or it's custom. And so far there is no RISC-V one. We are working on the draft.
It would be 8 registers.
Who knows? If you don't agree, you join the RISC-V Foundation, you write why you don't agree, and you discuss in the forums, and you can influence the ISA groups to go for 16, if you have a reason for it, or 4. So far, the majority is going towards 8. It's a trade-off between area and programmability and coding, and a lot of stuff.
And are there any other ways to exploit instead of as a historic array that is?
Other 3, or you can also do it serially, yeah? Having an instruction doesn't mean that the implementation is single cycle or efficient. You can serialize everything with a 1-bit multiplier. It will take a few months to do the whole multiplication, but you can do it. Other three are the multiplier tree are the let's say the other way of doing matrix multiplication competing with historic arrays. Welcome. But someone is using vector multiplier with the outer product algorithm, so a scalar times a vector and then you accumulate. You serialize in time and you accumulate. You don't need any 2D data path. This makes sense in case you're using these extensions within a CPU which has already the data path of a vector machine and you don't want to add the area. So you want to be compliant with the code so that you can execute matrix extensions, but you don't want to pay the area, except for the register file and the decoder. But if you don't want to add the historic array, you serialize it in vectors, in micro vector operations. Absolutely something we are having a look at. Okay, and this is how you do the matrix multiplication in C assembly. So you can tile your matrix multiplication with the tile that is as big as the size of your register file element, and then you do the normal algorithms that they explain you in Algebra 1 in the bachelor, and but it's at matrix level instead of a scalar level, but it's the same. Okay, so we are concluding the second last or the third lesson. Today we saw a lot of different custom extensions. I took most of them from the PULP extensions because they are open source. They've been verified. Now they are maintained by the Open Hardware Foundation. They are part of an open source CPU. They've been implemented in Silicon countless number of times. The compiler is also open source, and there's a lot of software written that can use and leverage these extensions. We discuss how these extensions have been defined. So I want you to take home that it's not a let's add an instruction, but it's an hardware software co-design exercise. When you actually deal with the real hardware, you want to be careful of the resources you're adding and being smart in optimizing your data path. And of course, when you're adding extensions, you need always to have a look at your context. So what is the domain? What is the application? What is the set of applications I'm trying to optimize? Do the profiling, as your colleague suggested the very first day of this series of lectures. Understanding exactly what you need. Implement them. Check the physical design. Check what the compilers can do, check at application level what are the benefits, and then implement them in your final design. So if there are no final questions, we meet tomorrow. Thanks.